Let's start recording. Just gonna quickly check Blackboard. Actually, I just want to make sure. See if Ashley's still registered. She's dropped and just hasn't told me. Which would be cool. Oh no, I forced added her to this, so that wouldn't work. No, okay, just not here. Okay, so I'm gonna continue on from where I was last class. So we ended last class talking about how we can make anomeric bromides using either HBr and acetic acid. And that was really straightforward. Or we had this kind of loopy way of doing it using the Apple reaction, which is a lot gentler. So cool. Let's say we've got our anomeric bromide. We're very proud of ourselves, however we made it. Hey, Ashley. So again, I'm going to use this notation that this is just benzyl protected everywhere. And because, again, I haven't drawn in any other substituent everywhere else, that tells me that this is glucose. Because I haven't sort of indicated that the stereochemistry is anything different than a standard. And a standard is glucose because it's just the default. So, standard ways to do this kind of thing. And so again, we've briefly discussed this reaction, and I should have given myself some space up higher. And I'll label it down below. So we could use a silver salt. The most common one is silver triflate. The reason we use silver triflate, instead, you can use any silver salt, it doesn't matter. Silver triflate is really, really soluble, and a triflate basically dissociates completely. Triflates are important for this class, so is anyone unsure? You know what, I'll draw it in instead of asking anyone if anyone's unsure. So OTF is this. So it's a sulfonate with a trifluoromethyl group. Triflic acid, the conjugate acid of this, is the strongest normal acid. Like there are these super acids, but those are just weird and silly. Triflic acid is the strongest normal acid that's really available. Okay. So what happens here is we've sort of seen this. We make a bond between the bromine and the silver. So the bromine kind of conjugates to the silver, and that's because silver and bromine make ridiculously strong bonds. Silver makes ridiculously strong bonds with all halogens. So maybe fluorine. I don't know about fluorine. Probably not. Fluorine's weird. This is then going to invert into the right boat. I'm not going to draw that because it makes my brain fry. I don't like it. So I'm going to skip ahead and just draw the oxocarbenium. But we drew that right boat in the last class if you need to revise that. Plus silver bromide. And that silver bromide is now going to start collecting at the bottom of your reaction vessel as kind of a brown-gray powder. And let's say then we have some nucleophile present. In my notes, I have methanol. We've been using a lot of ethanol. Let's stick with ethanol. We lost Susanna. I guess she preferred methanol. And so the ethanol attacks Oh, so Suzanne is like is a new graduate student in my group, so I actually don't know if she prefers ethanol or methanol. But by leaving the class, I think she might prefer methanol. She was speaking with her Zoom call. Okay, so we get the alpha. We've seen this a lot. We're going to get a bit of beta as well. And whether we get the alpha or the beta in here, if we start looking at the things we talked about last class, what determines the reactivity here? Again, let's think about what we have. There's no temperature written, so I'm just going to put one in here. We'd probably do this generally very cold. The reason you want to generally do these cold is the warmer you do them, you just have background hydrolysis. You have background. There's water everywhere. Like this is one of the things you learn as a sugar chemist is water's freaking everywhere, and it's awful because it wants to react with instead of your nucleophile. So cold slows that down, which is good. We look at whether we have anchiomeric assistance. We don't. We have benzyl groups everywhere. We don't have an ester at C2. So we don't have anchiomeric assistance. Our solvent is neutral. We're using dichloromethane. We don't have this ether solvent. We don't have the acetonitrile solvent. We have a neutral non-participating solvent. And there's nothing super special about the nucleophile or the promoter. Again, we use the, I think we discussed this like in class number 2. This thing here is called the promoter. It is the other word for catalyst, but sugar chemists are fucked up and weird, and so they call it a promoter. There's nothing special with the promoter leaving group pair here to make you think anything weird. We're going through an oxocarbenium. So, all that being said, it's positively charged. And then both of those are going to go, of course, to their respective neutral species getting deprotonated by some nearby ethanol. Okay. So, I actually have the precise ratio of alpha to beta written down here next to me, but I want anyone to guess which one's going to be dominant. You're going to have more alpha or more beta under these conditions. Anyone except Paul?
I'm guessing alpha.
Yeah. Why?
Because of anomeric effects.
Exactly. Like there's nothing weighing this anywhere else, right? So it's just pure anomeric effect. You have a good oxygen nucleophile, which is going to feel the anomeric effect. And so, yeah, you get a 2-to-1 ratio. The yield is about 85%. So this is a classic glycosylation. This is, it's called the Koenig's. I think I put this name up already. Nor glycosylation. And that's using anomeric bromides with a silver salt to activate them. Okay, that's good. Now, if I want to make this, we actually have some ways to make this more alpha selective or more beta selective. So if I want to go alpha selective, then what you're going to find is the best way to do that is to convert that anomeric bromide into something else. Well, we're actually going to convert it into the beta. We use tetrabutyl ammonium bromide. tetrabutyl ammonium bromide, John? That's a 4, sort of. That, I think we actually covered that in a previous lecture. That's going to convert that to the beta bromide. Now the alpha is more stable than the beta, anomeric effect. And so that equilibrium lies towards the alpha. But the beta then is more reactive, as we discussed. And so if you have a nucleophile, now notice that there's no silver salt here. So I needed the silver to make the alpha more reactive. The alpha bromide on its own wasn't quite reactive enough to react. So we needed that silver salt to kind of rip it off, make the oxocarbenium, that dechemistry. Without the silver salt, we have now an SN2-like reaction. And you know SN2s go with inversion of configuration. And what we're taking advantage of here, and again, if you flip back to previous lecture, is the fact that this is fast. This is slow. This is fast. So we have a fast equilibrium. The alpha and beta bromides switch back and forth quite quickly. But the alpha bromide is quite unreactive. The beta bromide is very reactive. So you make the beta bromide, it can react with the methanol, convert to the alpha methoxide, like alpha methyl glycoside. Whereas the alpha bromide, reacts much slower to make the beta methyl glycoside. So it's not, so this guy's sitting around, you can have methanol in here, you can have the tetrabutyl ammonium bromide, and this is going to be slower than that. So it's going to go to this is then going to react to that. So eventually everything is going to go to this, and you're just not going to make much of that. So the overall reaction conditions here is you take that alpha bromide that you made using either the Gehrig's, the Apple reaction or the HBr, acetic acid. You add tetrabutyl ammonium bromide. You don't need much, sort of catalyst. You add some methanol, and you add a solvent. Methanol, I know, is a solvent, but we're not using it as a solvent here. We're using it as a reagent. And that is going to lead to the alpha one. And this chemistry actually works really well. Like a lot of the chemistry, like a lot of the glycosylation chemistry I'm going to talk about in this course doesn't work all that well. And I think this is a truism of chemistry in that if there's a lot of ways of doing something, it means that none of them is very good. Because if any one of them was very good, then everyone would just use that and they wouldn't use the other things. But making these glycosyl bonds, there's a lot of ways of doing it because they all suck. And they suck differently. And sometimes you get lucky and something works really, really well for your system. For relatively simple monosaccharides and relatively simple alcohols, this is actually really, really good chemistry and really robust. So we can make an alpha selective one. What if we want to do beta selective? Well, here we've got two options. One is, okay, let's play with anchiomeric assistance. So if this whole thing is acetylated, and I add, silver triflate, and I add methanol, and I do this in dichloromethane. Sorry, what did I do? There we go. I've been using CH2Cl2. Somebody pointed out to me at some point that I should never use DCM as an abbreviation for dichloromethane. I should always write CH2Cl2. And it was somebody I respected, so ever since then I've been thinking about it and I always forget. but when I remember, I try and do it the right way. And so if we have this, again, we're going to have the same thing that happened up there. We're going to go to the oxocarbenium because the silver triflate and dichloromethane methanol thingy makes oxocarbeniums. But this time, we've got the Anomeric Acids. I know we've only seen this once, so I want to do it again just so everyone follows. We can draw it like that. And so what this again is doing is that acetate is blocking that alpha face. And so when our nucleophile is coming in, it comes in beta. So this works really, really well. And it's really, if you want beta, actually, if ever you want beta in this class, the best way to do it is just use Anomeric Acids. Don't fuff around with anything else. It's just so much more reliable than any other method. And yeah, you can get fancy, and we're going to see people get fancy. But getting fancy never works as well as just using Anomeric Acids if you possibly can. But there's a problem here. And that's mannose. It actually has a name called the mannose problem. Again, we're not very creative. And the problem with mannose, if you remember mannose, is you flip the nose. And so if we have an alpha bromide, which we're still going to make, even with mannose, and we use those same conditions, what do we get? Do you get an alpha or beta methoxy?
You would get alpha, right?
Yeah, why?
Because your acyl group is axial, so there's nothing blocking the face, and then there's nothing else directing selectivity. So
Yep. So that's exactly what happens. It's a little awkward to draw, so forgive my drawing. We'll fix it in the next structure. We have the oxocarbenium, you have the acetate at C2. Just, it wants to be there. And what that's going to resolve into is that. So again, we still have Anomeric Acids. It's just now the Anomeric Acids is on the top face. And so when your methanol comes in, it comes in from the bottom face. And now you've got alpha. Okay. Don't know if I fully see the problem here. But that's using Anomeric Acids, we get alpha. Okay, with mannose. And we do the other thing. Benzyl group, so no Anomeric Acids. And it's mannose, so I should draw in the fact that it's mannose. Note again, the convention I'm using here is I'm indicating that it's mannose because I'm just saying that, hey, everything else is normal. I am drawing in the one that's not. let's say we use silver triflate, DCM, methanol. What's my product of my reaction? Somebody.
Would you get mostly alpha again?
Yeah, you get almost entirely alpha because you have the anomeric effect, and now you have sterics with this benzyl group blocking the top face as well. Okay, so, the nice thing about the other sugars is that anchiomeric assistance can get you beta. And beta is slightly favored sterically as well because the bottom face is blocked by the C2 position. A little bit, even under neutral situations. So you've got a possibility of getting beta. The problem with mannose is that you have the C2 is up, so it's blocking a beta face. The anomeric effect gives you alpha. Anchiomeric assistance gives you alpha. Everything gives you alpha. So this wouldn't really be a problem, except the fact that the only mannoses that really show up in your body are, of course, beta. So if all mannoses were alpha, hey, who cares? Whatever. But mannoses aren't, they're mostly beta. Well, that's inconvenient. Okay. So let's say that you're sitting around, 1973, and let's say you're at a progressive university that is having women sitting around in organic chemistry classes in 1973. So Berkeley. So I guess we're still like, some ex-hippie is teaching or in your lab. And you're thinking about how do you overcome this problem? I think this problem was actually overcome in Austria, which is like the opposite of like hippie culture, but still. What conceptually, just thinking about this, how can you try and get yourself some beta mannose? Any ideas on just the concept, the reaction conception? You don't need reagents, you don't need ideas. Just how would you want to think about going about trying to solve that problem?
Somehow flipping that axial OH group, I guess.
But then it's no longer mannose.
Yeah.
So what we've done here is what we've shown is that if we rip off that bromine completely, go through an oxocarbenium, we get, and the other problem is, right, we had the other system where we could have done let's just solve, maybe this will help. This is just gonna be a lot more fun if you come up with this on your own. So if we try what the other thing we've seen, tetramethylammonium bromide, methanol, that's also going to give us alpha because, of course, the beta bromide is a lot more reactive. So that also screws us. But Conceptually, can you maybe see a solution that arises from that?
I guess you would need a less sterically hindered protecting group, like on the top, like where the benzyl group is.
You know, that's an interesting idea. I don't think it works because I think it's still more sterically hindered than the bottom, and the anomeric effect favors the bottom.
Okay.
But let's think mechanistically. What mechanism would give us beta? Because what we have here is oxocarbenium,
Twist,
oxocarbenium.
twisted chair, maybe.
Well, okay. And what would that do?
That will allow the methanol to attack from the beta end.
Okay, what do you want to attack on?
The carbon attached to bromine.
What form? Okay, the carbon attached to bromine. Do you want the bromine still attached?
Yeah. It
Yeah,
would be the quick SN2.
right. If we can do an SN2, then we know we get inversion of configuration.
Yes.
So if we can do that, then we can get the beta. And then we can celebrate in a 1970s style with a jellied salad. But we need to figure out how to do this. So the way that's worked is we know that silver triflate rips off that bromine. So what if we use a weaker form of silver? And that's what is done actually with this. So if you take, I'm getting really sick of drawing this freaking molecule. And we take silver solid, silver nanoparticles basically, and methanol. Note that we don't have a silver plus anymore. Now this is silver 0. So, bromine is going to interact. Like we're lengthening that bond, and it's interacting with the silver 0. But this is silver 0. And so we're not positively charged here. Everything's just kind of, delta plus. We can put a delta plus on here and a delta minus on a silver, I guess. And what we've just done, of course, is we've activated this bond. We have weakened that bond. And so now where methanol didn't have a chance of displacing this directly, now it can. So used to drawing alpha. So, and there's some Br minus floating around, and then silver 0 still. This works. This actually works really, really well. And it's, I think, one of 3 ways to make a beta mannose that we're going to see in this course, or beta talose. Talose is mannose, but you flip also C4, or if you have any kind of axial C2. They're just a pain in the ass. You have very few ways to make them. This is one way to do it. Yeah. So this is actually, I got the date wrong. It's 1983. This is much more recent. If anyone wants the paper, it's Garrig who did the iodinations. Published in Acta Scandinavica, Actica Chem, so the Scandinavian Journal of Chemistry. B, 1983. page 37. There probably weren't very many pages. So it's to me that still seems reasonably recent that we have this solution to this problem. Because before that we really did not have a way to make beta mannose. So it just really wasn't synthetically accessible. You just couldn't do it. So I started with anomeric bromides, and we still use them in the lab, but anomeric bromides are basically old technology. Maybe crude technology. They're easy to use, which is great, but really unstable. So they kind of, if you leave, to be honest, the galactose version of this with the 4 acetates on it and the bromide, if you leave that out on the bench open to the atmosphere for about 5 hours, it decomposes completely because it starts generating HBr, and then the HBr degrades more of it, and the whole thing just falls apart really quickly. So you have this beautiful white powder when you start. In the morning, you leave it out, and it goes to crap. It's okay in the freezer under argon, but it's pretty nasty. So fast decomposition. The other problem with them is make them, use them. So that's not how you spell use. Can't carry through. So you can't do any chemistry on an anomeric bromide. You need to use immediately. Which is a little inconvenient. So you need to make them and then use them. It needs to be the last reaction you do before you glycosylate is to put the bromide in. And that's not as easy. So what we want is we would like more stable versions of this. And everything else we're going to talk about now is going to be much more stable versions of these, things that you can carry through chemistry. Okay, so right before, that was the way of doing it. And so somebody came up with the idea of using glycosyl fluorides. Move around the periodic table a little bit. So this is in a German journal. 1981. 431. Page 431. So this is Mukayama. He's famous for silicon chemistry, actually, most of what he's done, but he did some sugar chemistry too. And what he found was that you could take the hemiacetal. So again, this is a hemiacetal with one OH, and one oxygen's in an ether, the other oxygen is OH, it's a hemiacetal, because it's not a full acetal, because a full acetal has both oxygens making ethers. This one, only one of them is, so it's hemi. And you react it with a reagent. Which has way too many fluorines on it. This reagent is called DAST. And I'm never going to remember what that stands for. Notice there's no F in DAST, which is very confusing. There should be an F.
Dast. Like just add an F at the end.
Yeah, we could. I don't know what I have no idea what that stands for. Diethyl amino thio or sulfur trifluoride. Maybe it is trifluoride.
That's what I was thinking. But
So dast, but then nobody will know what you're saying, and that sounds stupid. We wouldn't want to sound stupid. So I'm just going to talk about exactly how. Okay, that's good. That's clever, Ashley. You know what? We need to create a faster reagent that has an electron drawing nitrogen on it. We will call it fast. That's really clever. So if you remember how sulfur reacts, sulfur works not through SN2s, it works through addition elimination reactions. So you add to sulfur and then you eliminate. I'm going to come back to where that proton went. So give me a second here. So then that loses a fluoride. To fast. It's been a long day. I think that might actually be funny. I'm not sure, but right now it's absolutely fucking hilarious. So we get F minus. And now we're going to do an SN2. So there we made our anomeric fluoride, but we're not done yet. Let's just take care of this other component. I'm going to do a little bit of, electron accounting. Normally I don't care, but I just want to come back to why this actually works the way it does. So I don't know, some of you might be familiar with DMSO, sulfur double bond to oxygen. That's pretty stable. That's where this guy's going to go. So it's going to release another F minus. And normally the solvent for this is THF. And so now you have F minus floating in THF. That's not a bad base. And so what we have is our active species isn't actually the alcohol I drew there. Something more like this. Now I'm going to just draw this as an ion pair. You can judge where that hydrogen is, but that fluorine is going to associate with that hydrogen. It's going to make that oxygen negative. And we know that O minus beta is better. And so this reaction, you know what the problem is? This is meant to be a squiggly line. This is meant to not be a squiggly line. So we tend to make the beta because what we end up really having is almost an O minus that can then flip back and forth between the alpha and the beta, but prefers to sit beta. So it sits beta, and then eventually it reacts with your DAST to give you the product of this intermediate, which then decomposes to give us, reacts, loses the fluoride, fluoride comes in alpha, so we get these alpha fluorides.
so beta is better for that hydrogen F minus interaction. That's what you're saying.
Beta is better when this is O minus. O minus is better at the beta position to the alpha
Right.
position.
That makes sense. And sorry, I had another small question.
Yeah.
About the very first arrow when you're dissociating that, or like taking off that fluorine. Was that supposed to happen? Because the next step you show 3 fluorines as well.
No, there's only 2 here.
Oh no, I mean
up here. No, I lied. Yes.
yeah.
Yes. Absolutely.
Cool.
Now, there we go. Now I'm trying to find my rest of my notes on anomeric fluorides because I inexplicably shoved them somewhere else, which sounds like me. Oh, here we go. There we go. I hit it. That's really stupid. Why the hell did I... Okay, whatever. So, we can make them this way. So we can make them from the hemiacetal. Another way we can make the anomeric fluorides is we can make them from glycols. And what the hell is a glycol? So I just love some of this chemistry we're going to just do right now. And because we're going to actually use glycols themselves as well. So if you take our favorite bromide that we've just gone back to, and you treat that with zinc and acetic acid. So it's zinc metal. That's just 2 dots for electrons. Okay. Now, I still have trouble with this, and it's because I'm an organic chemist, and that means I'm not very smart. And so I get very confused about what happens here, because to me, metals are electron poor. That is what metals do. And so when a metal is electron rich, I get confused. And this metal is electron rich. So zinc is actually going to act as a nucleophile. And like silver, zinc loves itself some bromine. I am supremely unhappy at this moment. That is why I'm putting it in brackets, because I can pretend it doesn't exist. And I don't know how charges work. Okay. So, what do you think about the stability of that negative charge?
Bad.
Yeah. I don't think it exists. I know that some people do think it exists, which is why I've drawn it in a bracket, but I disagree with them and they're stupid. Like, I'm unhappy enough about the zinc thing, but I'll grant that. But this is not a real intermediate. How can we take care of that? You know, mafia style. What are our options here to take care of this negative charge?
You could spread it out.
Yeah, I like the idea. How do you spread it out?
Form the double bond.
To where?
With oxygen. Or
Sorry, can't do that.
Maybe
Options
not.
are using 4 orbitals. I can't accept more. But I like your idea about a double bond.
maybe the other way, and then the acetyl can act as a leaving group.
Perfect. Yes, absolutely. Sorry, I was like pointing dramatically in there and just really excited.
I'm upset that I missed it. So.
Yeah, I know. There's no camera. Exactly. I should probably turn a camera on for that. This is one of those times when I should have candy with me and spread candy around. It feels kind of condescending to do that, but everyone likes candy. I like candy. Okay, that's exactly it. So we're basically going to expel the acetate. This is a glycal. So it's a double bond. Anyone who's taken the 331 or currently taking the 331 course, you might have come across molecules like this. This is called an enol ether because it is both an enol in that it is an oxygen next to double bond that really wants to be a ketone, and it is an ether because that oxygen is attached to a carbon, and so it's kind of stuck to be like that. These are enol ethers. And we're going to play around with the advantages of what we can do with these in a bit, with glycals in specific. We can make glycals. Sorry, we can make fluorides from glycals. I need to come back because my notes are all fucked up, and so I have to go back a bunch of slides. There we go. No, 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 back more. Here we go. How was it? 448. So the way we do this, I'm actually just going to leave this slide as is because if I try and draw anything else on it, it's going to get really confusing. So the nice thing about glycals is they're really stable. So what I'm actually going to do now is I want to put a very, very brief digression into protecting groups. So what we need to do is we need to swap this for a base stable protecting group. So we don't teach protecting groups, I think, in any of our classes, which is kind of silly for the amount of time that we spend. We do so much. Let's face it, carbohydrate chemistry is protecting group dancing. And that's really what we're going to be talking about. So we're going to talk about a bunch of different protecting groups in this course, probably in the next bunch of lectures. So we have the ones we've seen so far, acetate and benzyl. The other common ones we're going to see are benzoyl. This is kind of like an acetate where instead of a methyl you have a phenyl. And benzyl versus benzoyl. I think if you have like an Australian accent, it's very, very clear. With a Canadian accent, that they sound really, really similar. And if you try and listen to somebody from the American South try and pronounce these things, you can't tell the difference. Although that might be the least of the problems because I don't understand a lot in that drawly accent. Terbutyl disilane. So these are the silicon protecting groups. The wavy line tells us where the separation is. You know what? Maybe I'll try and do the wavy line in a different color. It's like the group is everything on one side of it. Trimethylsilyl. It's what I find always really confusing is tetramethylsilyl has exactly the same abbreviation, and you just need to know by context whether it's tri or tetra. And if I think about it too much, like this is a really inside baseball field where it really sometimes sounds like we're talking to ourselves. Acetonides, we've already encountered them. Again, isopropyridine is the same term. I don't think I've ever actually written isopropyridines as a plural. I think I always call them acetonides. Interesting. Okay. And the idea there is that you can have 2 oxygens attached. So again, the protecting group is that dimethyl, that 3-carbon piece. We're going to talk about distannanes, which is tin. So if you have 2 oxygens, well, they're really stannanes. They're just divalent stannanes. There's only 1 tin. There's not 2 tins, which distannane seems to indicate 2 tins, but there's only 1. That's weird. Benzylidines. I've seen it spelled both with an I or with a Y. I think both is fine. I don't know what the IUPAC one is. Again, this is another one where we have two alcohols adjacent to one another. And it's a benzyl, but it's like from benzaldehyde instead of from benzyl alcohol. So it attaches to 2 different alcohols next to each other, and you get this phenyl thingy. Boronic acids. You're going to see a trend here. We kind of have these mono blocking ones and these di blocking ones. I'm putting a protection group again in red. And some of my favorites, parabenzyls. And there's 2 of them. They're kind of a matched pair. We got the nitro, and we have the methoxy. And you can make benzylidines or benzyl protecting groups out of both. There are, tons more. These are what I think we can do everything you would ever need to do in this class and more with these. Benzyls, not phenols. Shit, my color's wrong. So these are, I didn't draw acetate or benzyl. Hopefully people are comfortable with those too. This is the protecting groups we're using in this course for the carbohydrate side. And they each have advantages and disadvantages, and I think we will probably I'm going to probably copy this slide and stick it on in front of something else, so we'll come back to that. Oh, no, that's not how I do this. It's one of your assignment questions, is to look at the stability of these different protecting groups under conditions. We're gonna go through some of them in class, but some of them I think you're gonna want to check and look up and how you can put them on, take them off. But for this, what we wanted to do up here originally is take off the acetates. Sodium metal and methanol is a good way to do that. Also call this sodium methoxide in methanol. That's going to hydrolyze methanylize, I guess. You don't hydrolyze in methanol. And it's still fucking boat. Going to go to the OHs. So we cleave off everything. And then we put the benzyls on. Benzyl bromide, sodium hydride, THF sulfate. This works really well. This chemistry is really, really good. It works great. It's just you've done 2 steps and you really haven't done anything. Like you've just swapped one bunch of extra carbons attached to your molecule for another bunch of extra carbons attached to your molecule, and actually a whole bunch of extra carbons. Like the sugar only has 6 carbons on it. Each of those benzyl groups has 7 carbons on them. So you're like most of your molecule is protecting group at that point. And you try not to think about that too much. Okay. And the reason we're doing all that garbage is because we want to make an anomeric fluoride from a glycal. This, and I am blanking. I think this is Danishevsky's reagent. And I'm going to come back Sam Danishevsky is a complete and utter asshole, but he's done a lot for carbohydrate chemistry. And so this actually allows us to make alpha mannose from here. And I am going to, because my notes are a freaking mess, I'm going to return to this next class because I need to look this stuff up again because I seem to have just deleted that part of my notes. What I want to talk about now is once we make these kind of anomeric fluorides. And again, everything else is benzyl here. The advantage of this, what we can note here, one of the nice advantages of this approach, and we'll see the other way where we can actually get the beta fluoride by changing the reagent to a slightly different reagent. And this is all epoxidation chemistry, but I just want to make sure I draw it right. Is that you have a benzyl at every position, but you have an OH at C2. So if you want to do something with your C2 position, you can sort of substitute in an OH there without having to do a lot of crazy chemistry to protect everything else and get that one deprotected because it's naturally deprotected because you're introducing it late in the step in the synthesis. But what we want to know is what we can do once we have these anomeric fluorides. The nice thing is we've got really quite good control over them. So if we take this, I don't know, THF seems like a good solvent. And we think about, this is an odd reagent. It's tin tetrachloride with some silver triflate. Okay, I know that silver likes binding to halogens. Silver doesn't feel particularly strongly about fluorine because fluorine is like a weird halogen. Fluorine's like only like a halogen by technicality, and it's like an honorary halogen. It's not really a halogen. So as much as it's tempting to take the silver triflate and dump it on a fluoride, that's probably why they tried that first. It didn't work really well. What actually works really well is it binds to the chlorine of the tin tetrachloride. So what you end up getting is silver chloride and basically tin trichloride positive, and there's a triflate somewhere. And yeah, maybe it's coming on and off the tin, but it's not going to bind very well to the tin. Now we have a situation, and again, nothing new under the sun. It's just patterns, right? Everything is a freaking pattern. Is the fluorine combined to the tin? that fluorine is technically positive. Can't allow that to last. So we're going to go full oxocarbenium on that. And now what controls chemistry? Well, everything that you've already seen. So whatever else we add in here, like if we added some methanol in here, that's a benzyl protecting group. That's an oxocarbenium. We can basically ignore everything else that's happening here. We're back down to the simple fact that we have an oxocarbenium in the presence of methanol, and that's going to give us about a 2-to-1 ratio of alpha to beta. Because that's the way it works. That's not particularly useful. You know, nobody wants a 2-to-1 mixture of stuff. So what we'd really, really like is some better control. And so we can get that. So if we have that fluoride, and we're going to see a lot of this reagents. These are like, there's 2 of them. We're going to basically, they make their appearance here for the first time. They show some theme music or something. So this is BF3 etherate. It doesn't actually have a fancy name. It's BF3 etherate. And what it's going to do is, we're in ether. It's kind of gentle with the fluorine. And so we're going to favor this SN2 kind of thing, because you can imagine, I don't know if any of you have seen BF4. That's a thing. It's a pretty stable anion. And so boron doesn't really mind becoming BF4. And so this is a Lewis acid. Again, we're going to get back to this language. This is a promoter. So we lengthen that bond. I'm going to be a little squirrely about my where my charge is. I'm not really sure where to put my charge. I'm going to keep everything neutral. We're going to pretend all the bonds are dative at this point. But you could imagine putting a positive charge on the carbon here and a negative charge on the boron, or a negative charge on the fluorine. Both those would be appropriate and fine. But we're lengthening that bond, and now we're allowed to do our SN2. And again, the nice thing about the SN2 now, just like we were talking about the mannose, is we have control. Alpha goes to beta. If we made the beta fluoride, and we're going to talk next class and remember what the reagent is. You might ether looked weird up there. It's because I drew it in the backwards order. E22OH makes a lot better than OET2. They're both right. It's just that one is weird. Then this is going to give the alpha. Exactly the same logic. So suddenly we now have control, and it's independent of the anomeric effect. And it's independent of antiomeric assistance. Notice we don't have any antiomeric assistance. So we have this controlled SN2 reaction here. And again, the nice thing about these fluorides is, unlike the bromides, they're stable. You can have the joy of doing column chromatography on them. You can do other chemistry on the molecule within reason, and they'll survive it. So you have this option. But yeah, could you actually hear the quotation marks?
Yeah, I heard the sarcasm physically.
Yeah, it's good. Something's still coming across with this whole Zoom format. The other thing we can do is the second Lewis acid that we're going to spend a lot of time playing with is not as useful for this guy, and that's Tms Triflate. So we just saw TMS in our list of protecting groups, trimethylsilyl. Triflate, well, we've seen triflate. So this is like a silicon plus, basically. And silicon plus is a lot like carbon plus. And carbon plus is bad. Except we know that silicon plus freaking loves fluorine. Like, there's nothing silicon likes more than fluorine. You know, silicon fluorine bonds are really strong. Yes. I don't know what else to say. So unlike the BF3 where we're kind of doing an SN2 kind of thing, this is going to go all SN1. So this came into my vocabulary because I was at this classical music concert. I don't know, probably like close to 15 years ago. And it was a Schubert concert. And this guy next to me turned to me near the end and he said, you know, Schubert's got the skills to pay the bills and Schubert's the bomb. And just the way he delivered it, like there was no sarcasm, there was no irony at all. It was just like, this is the absolute appropriate language for describing what I have just heard. I now can't get it out of my head. So it's like an internal inside joke with myself, but I still, like, this is really strong. Super strong. So lame professor joke, if that's the only way to remember this, I don't give a shit. But silicon fluorine bonds are really, really strong. So when you mix TMS triflate with a fluorine that is kind of on its way off anyways because it's an anomeric fluoride, it shouldn't surprise you that you're going to get some silicon plus. There is a fluorine nearby. That's not going to do that kind of maybe sort of thingy thing that we were doing with the BF3. That is going to make a freaking covalent bond. Doesn't matter if this is alpha or beta. I've drawn beta because I felt like it. That's neutral now, except the fluorine is now positive. That is not going to last any length of time because I can't think of anything worse in this world than a positive fluorine. It's not really positive. It still has 8 electrons, but you know what I mean. So let's get rid of it. Solve that problem. We can all breathe easy, and the silicon is like really, really happy because it's got fluorine. And we have an oxocarbenium. And now it does everything an oxocarbenium is expected to do. So again, if we did this in CH2Cl2, we would get a 2-to-1 mixture of alpha to beta. Because it goes to the oxocarbenium, the protecting group is the same, the sugar is the same, everything is the same. It doesn't matter how you get the oxocarbenium. If you make an oxocarbenium with glucose, with benzyl protecting groups, and methanol is your solvent, or methanol is your nucleophile, it's 2-to-1. Basically, if it's almost anything, it's 2-to-1. If your nucleophile is really, really hindered, you'll start favoring the beta a little bit more. But there's not a lot of flexibility there. And because fluorine's weird, and what's really nice is what we're going to see in a lot of the reactions is that we're going to keep seeing BF3 etherate and TMS triflate. They're, like as I said, they're kind of the stars of this. Okay, no, galactose is the star of this course, or maybe alanine. But these guys, they're like recurrent characters, like the neighbor in a sitcom or something. They're going to keep showing up. And so the problem is that they react with a lot of things. So what we'd really like is to have something that reacted with the fluorine and not really with anything else. And the silicon's kind of promising that way because it's like silicon makes really strong bonds with fluorine. You just spent a lot of time talking about that, and that's absolutely true. But it's still silicon plus, and it's pretty freaking reactive. So we're lucky because we do have an option. We're unlucky because it's really toxic. But the Lord giveth and the Lord taketh away. Lead triflate. Still do THF and methanol. Now, lead, you don't see a lot of lead when you're doing chemistry. I had this cool reaction I'm trying to publish actually with that we use lead. It's like a lead-based cross-coupling reaction. It's pretty neat, but it's not catalytic. Like the lead doesn't turn over, the lead gets consumed, and it's pretty expensive, and then you create a lot of lead waste. So I have really no idea why anyone would actually ever want to use it. But mechanistically, it's pretty cool. Anyways, that's not what we're talking about here. We're talking about lead triflate. And so, again, actually, it's not catalytic, and we're going to create a lot of lead waste. But it's useful because lead makes pretty good bonds with fluorine, and it doesn't really interact with anything else. Lead oxygen bonds are pretty weak. Lead nitrogen bonds are really weak. And so lead fluorine is actually an okay system. And the nice thing again about this is, like the BF3, I'm going to write LX here, or OTFX. I'm going to be very unclear about how many triflates are currently attached to lead because I actually have no idea, and I'm not sure anyone does. But we have this interaction now happening. And so this is going to go SN2-like. And we have this exquisite control because, again, we have the SN2. Check. Specific for fluorine. Toxic as hell. Check. So, you have options. It works, and depending what else is going on, you might not reach for your lead triflate. It's also a lot more expensive than anything else. But it does work really well to give you this SN2 control of fluorides. And this course is all about paper chemistry. So who cares about toxicity? Toxicity is a worry for real people. I think I'm going to leave it there because I want to come back to making the fluorides from glycols and the two different ways to do that. And I don't currently have my notes on me. So I think the one thing we just want to emphasize here, I want to put in the notes, you're all here, so it's not like I need to say this for somebody else. But I have no idea if you're paying attention. Fluorides are stable. Are more stable than bromides. It's why we're interested. The other problem, though, is fluorides are more explosive. And so there have been a few incidents with glycosyl fluorides exploding. So not the best. But even better than fluorides, glycols are real stable. And we're going to come back, and once we resolve how to make alpha and beta fluorides from glycols, we're going to talk about what else we can do with glycols. Because there's a lot of chemistry that you can do with glycols. And glycols look like a good solution for a little while, and then everyone got excited about something else. So we're going to walk through 3 more examples: glycols, trichloroacidimidates, and the sulfur-based ones. And then we're going to move on. So I think that's going to be 2 more lectures, hopefully. And I'm not going to spend, a month talking about glycosylations, because I actually do want to talk more about what we can do with chemistry, with these kind of things, and put a little bit of biomaterials into the course this year. Okay, I'm going to leave it there. We're a few minutes early. I don't know if there's any questions I can answer questions, I guess.
So if you had the beta fluoride or the beta fluoride, I'm assuming you would get the alpha product.
Yeah,
then?
with lead. Yeah, it's SN2. Yeah.
And what does it say in the second check mark? Like specific.
Specific for glycosyl fluoride.
Thank you.
Sorry, it says Dr. Chance chicken scratches. I'm going to blame this on the fact that I am writing on a tablet. And I'm going to know that the truth is that my handwriting is probably neater on the tablet than it is in reality.
My handwriting's hot garbage, so I can't really judge you.
Yeah. Then you should go for a PhD. I got the excuse of being a doctor. Of course, my handwriting's shit. Anything else?
Oh, yes. Do you remember when we had that example? I'm trying to find it, but where we had the acetyl group on the top face that was blocking.
Yeah, I think we had a Manos example for the back.
Do you mind just going back to that slide just so I can see how
Nope.
you drew it? 'Cause
Yes, I do. No, I do not mind.
it was at the start of the Manos problem.
Yeah. Here, the Manos problem. I drew this really awkwardly because it is kind of like pseudo-axial because it's kind of sticking out towards you. But if I draw it straight up, then it's really on top of everything else.
Yeah.
I kind of drew it off to the side and went all isometric on it, but it looks like shit. So I'm sorry.
I don't think there's a good way to draw that.
There isn't. I can tell you from experience that there isn't. The way that would be better if I hadn't written the acetate up there is I can live. This is actually more accurate than the way I'm going to draw it here, but I can live pretty comfortably. I'm going to tuck everything else off here to the left. I can live with that. But it looks it's actually a bit more, but it's not really axial. And that looks really axial, so it's kind of incorrect, but because the axial one is really down here. Pseudo shit. I also have to upload, I think, our last class's notes as well. I don't know if anyone's put some thought in. I know Samara actually mentioned the review article at the beginning of the class, but I don't know if either Kirsten or Ashley, if either of you guys have thought about whether you want to do a presentation or join in on the article. I'm assuming the presentation because I haven't heard from either of you.
Yeah, I was thinking about just doing the presentation. Are all of the grad students doing an article?
They have to. They don't have a choice.
Okay. All right.
They have no options. You have options.
So I could hop in on the review article with
if you want to do that instead.
Oh, okay.
But you
Gotcha.
probably need to make a decision relatively soon.
Yeah. Okay.
Do you want to do the presentation?
Yeah, I'll probably just do the presentation.
It's easier.
Yeah.
Okay. Ashley, do you have an opinion?
I was just going to do the presentation.
Awesome. Okay. There's only 2 of you, so I've done this in pairs in the past when I've had much larger undergrad groups.
Okay.
If you guys want to do it as a pair, you can. That's fine, or you can do it independently. I don't care, one or the other.
Okay. Well, we'll chat, Ashley. And then...
Yeah, if you guys want to chat and you guys can figure it out, because it's not like I'm gonna say the rule and like, oh, there's only 2 of you, so you have to do it independently. If you want to do it together, because that keep the workload the same.
Okay.
I'm fine with that. So that leaves the 3 grad students. So if you guys are doing an article, you can do it as a group of 3. And so you guys need to agree on something.
Yeah, that's fine with me. I know,
Unless one of you guys wants to go alone and do like lone wolf thing, but I don't
Yeah.
suggest that.
I know like Susanna and me talked about like collabing on that. I don't know if Samurai would want to do it as a group of 3, but
Yeah, we just kind of agreed to work together, but we haven't thought of any ideas yet.
the future's scary.
Yeah.
Sam, what's your opinion? Do you want to work in a group of 3?
No hard feelings if you don't.
She unmuted, but then she's not saying anything. So if you are
Hi,
saying
can
something,
you hear me?
yeah, I can hear you now.
Hi, yeah, I said group is great.
Okay. So group of 3, there you go. You guys can have a chat offline and figure out what kind of things you want to talk about. The only things you can't do the paper on are you're not allowed doing it on carbohydrate vaccines because we just had a paper on that. You're not allowed doing it on unnatural amino acids for autoimmune treatment because we had one on that. You're not allowed doing it on the conversion of carbohydrate biomass into nitrogenous heterocycles because we had one on that. That's really oddly specific. And I doubt that would be one of the things you'd come up with. And you're not allowed doing it on cancer probes based on cyanine glucose dyes. You can do other types of cancer probes based on glucose if you like. So those are the subjects you can't do because those have already been done. Anything else is good. Ideally, we'll have a chat about it, like because again, part of the whole purpose of this is that the 4 of us take this through and publish it. And so I'd like it to be publishable. So I'd like it to be on something that hasn't been reviewed extensively in the last 3 or 4 years. So we're kind of like in a new space and something that's had research done on it in the last 3 or 4 years. So we've got something to be published here. So that's your brief, and you can sort of pitch ideas back and forwards, whatever makes sense. I don't really care what the subject is. I knew nothing about conversion of biomass to nitrogenous heterocycles before we wrote a review on it. So I'm comfortable writing it on absolutely anything.
Are the topics, are they like, does it have to be like sugar chemistry or?
It can be amino acid chemistry.
Okay.
It can be bioorganic chemistry. I'm okay if it's lipids. It can be, biomaterials, I guess. I think I do need to say it needs to be in the area of bioorganic biomaterials. So we can't sort of do palladium cross-coupling of aryl systems for new catalysts, for example, because that wouldn't fall within the scope of the course. But still, I'm really willing to be very broad with my definition of bioorganic.
Okay, cool.
Okay. Sounds good.
Yeah. And if you guys have a bunch of ideas you want to run some by me, we can sit down and chat.
Yeah. We should probably get together and like brainstorm first.
Yeah, you
And
probably.
then, yeah.
Okay. Thank you. We're done.
Just before I go, John, I just wanted to remind you that about the cannabis meeting, like conflict, like in the morning.
I moved it. I moved the cannabis meeting.
Did you? Okay.
You should have gotten. You should have gotten a update on that.
I probably did. I'll check.
I'm just making sure I did. Yeah, I moved it, but where'd I move it to? Oh, okay. I moved. We just don't have one next week. It's now Friday mornings at 8:30 every second Friday,
Okay, cool. Yeah, I see it.
starting on the 12th of February.
Sweet.
Yeah. Okay.
Take care.
Yeah, thank you, everybody. I will leave that there.
Thank you. Have a good weekend.
Yeah, you too. Have a good weekend. I'm gonna put up a couple papers. I think you don't need to read them. They're just background, but they might make sense of stuff if you want to look into some of these glycosylation things. Okay, bye.
Bye, everyone.
Bye.